We're going to take a closer look at elements. Elements cannot be broken down into simpler substances by ordinary chemical methods. At present, there are 118 elements that are recognized on the periodic table. 4 of those elements make up 96% of the human body. Carbon, hydrogen, oxygen, and nitrogen are those 4 elements. Every element is composed of atoms, and the physical and chemical properties of atoms match that of their element. When we talk about elements, we're talking about the simplest forms or parts of a substance, whereas a molecule is a combination of elements, like water, which is made up of hydrogen and oxygen elements. So let's talk more about atoms. Atoms are unique building blocks for elements. Atoms are the smallest units of matter, because elements are also units of matter. But the smallest part is the atom. On a periodic table, you can see the chemical symbol for an atom, called the atomic or chemical symbol, as a 1 or 2 letter shorthand. For example, C is for carbon and K is for potassium. There's other information you might also see on a periodic table, like the atomic number, which is the number of positive protons in the nucleus of an atom. If you want to write this in, say, a sentence in a paper, you would write the atomic number as a subscript to the left of the atomic symbol. Mass number is the total number of protons and neutrons in a nucleus, so it's the total mass of an atom. And if you want to write this in a paper, in a sentence, you would write it as a superscript to the left of the atomic symbol. An atomic weight is the average of mass numbers of all isotope forms of an atom. Now, this information in this quick guide introduces a lot of terms, so it's a good slide to come back to once we've talked more about atoms. Here's a periodic table of elements just to get a quick look. You can see all the chemical symbols with information like atomic number or number of protons, and atomic mass is reported. When we're talking about atoms, we want to start with, what are they made up of? Well, atoms are composed of something called subatomic particles, and there are 3 subatomic particles: protons, neutrons, and electrons. The protons and neutrons are located in a central region of the atom known as the nucleus, and the electrons are located around the nucleus in what we consider orbitals or orbits. When we look at what to add together to figure out what is the mass of an atom, well, we only want to add together what weighs something. AMU is used as an arbitrary measurement, known as atomic mass unit, to let us know that protons and neutrons are bigger than electrons. Electrons are so small, we say their mass is negligible. So in order to get the mass for an atom, we're just going to add protons and neutrons, which both weigh 1 AMU, together. We don't add electrons to get atomic mass because they're too small. You can also see the charges for protons, neutrons, and electrons. Protons have a positive charge. Neutrons are uncharged, or you can say they carry a neutral charge, and electrons have a negative charge. Here are just 3 examples of atoms: hydrogen, helium, and lithium. Hydrogen with 1 proton and 1 electron, helium with 2 protons, 2 neutrons, and 2 electrons, and lithium with 3 protons, 4 neutrons, and 3 electrons. You can see the protons and neutrons, if present, are located in a central nucleus, and the electrons are displayed in orbitals. And we're going to mainly be talking about balanced atoms. So the number of positive protons is going to be balanced by the number of negative electrons, so the atoms are going to be basically electrically neutral. So if you know the number of protons, you know the number of electrons. Remember, protons and neutrons are in the nucleus, electrons are in orbits, and we're going to look at some more examples of atoms. There's 2 different ways to study atoms. You can use the outdated, kind of simplified planetary model. It depicts the electrons in orbits. That's what we've seen thus far. It's very useful for learning about atoms. It's still useful for illustrations because its orbits are more 2-dimensional. But really, those orbits are 3-dimensional structures. So the orbital model, which is the current model used for looking at atoms, is more correct. It's going to show electron clouds. It's going to show these regions where it's probable we're going to find an electron. So here you can see the planetary model on the left and the orbitary model on the right. The orbital model or orbitary model is going to be most correct, but it is easier to study and learn from the planetary model. So what have we learned thus far? Well, to identify an element, we really want to know its atomic number, which is the number of protons. Protons have a positive charge, neutrons are uncharged, and electrons have a negative charge. And if we want to get atomic mass, we have to add together what actually weighs something. So we want to add together the number of protons and the number of neutrons. Since the number of protons is the same as atomic number, you could change the mass number equation to atomic number plus the number of neutrons. It'd be the same thing as number of protons plus number of neutrons equals mass number. What we haven't thus talked about yet is isotopes, and those are going to be varying forms of atoms that make up an element, and they only differ in number of neutrons, so that's going to change the mass number. So let's look a little bit closer at mass number. Here we have a carbon atom that has 6 protons and 6 neutrons. Each one of those protons and neutrons weighs 1 AMU. We're not concerned with electrons because they're too small to have a mass that we want to count. So to get the atomic mass for this carbon atom, we just add the number of protons to the number of neutrons. So 6 plus 6, and that equals 12. And when it comes to isotopes, we're going to be looking at atoms that are structural variations of the same element. These atoms are going to contain the same number of protons but different numbers of neutrons. We actually take an average of their atomic mass in order to get something called atomic weight. That's an average of relative weights or mass numbers of all the isotopes of an element. And what we see is the atomic weight tends to look like the isotope that is most present in nature. For example, let's look at hydrogen, deuterium, and tritium. These are all 3 hydrogen. They all have 1 proton. And the number of protons tells us what atom we're talking about. If I were to change the number of protons, its atomic number, I would be changing which atom I'm talking about. But the difference among these 3 isotopes of hydrogen is the number of neutrons. Hydrogen has no neutrons. Deuterium has 1 neutron, and tritium has 2 neutrons. And so that's going to affect their atomic mass, because to get atomic mass, I add number of protons to number of neutrons, and that's going to be roughly 1 for hydrogen, 2 for deuterium, and 3 for tritium, which is where their names come from. A lot of times when we're naming isotopes, we'll just say hydrogen 1, hydrogen 2, tritium 3. The number that we use is its mass number. But for hydrogen, the naming system is just a little bit different. And if you were to look back at a periodic table, you would know that the atomic weight of hydrogen is reported as 1.008. So that actually reveals that the lightest isotope, hydrogen 1, or the first one we call hydrogen, that's going to be present in much greater amounts in our world in abundance than either deuterium or tritium or hydrogen 2 or 3. So what we note is, just like if you were to take an average for a classroom, the most abundant grade or the most abundant isotope in nature is going to dictate more what that average looks like, what that atomic weight looks like. So atomic weight or mass is just an average number. So for example, there are carbon 12, carbon 13, and carbon 14 isotopes. They all have the same number of protons, but they have a differing mass. And that number, 12, 13, and 14, actually tells you their mass. The mass number for carbon 12 is 12. The mass number for carbon 13, 13. The mass number for carbon 14, 14. The only difference between them is the number of neutrons, but they are atoms of the same element, carbon. Now, if you were to look on the periodic table, the reported atomic weight for carbon is about 12.01. That means that carbon 12 is much more common in our environment than carbon 13 or 14. And so that means that when we take an average of all these isotopes and how many there are in nature, it's going to be the most present, the most abundant isotope that dictates much of what that atomic weight that's reported looks like. So in summary, for any element, the number of protons dictates what atom you're talking about. The number of protons is the same as the atomic number. If you know the number of protons, and you're talking about a balanced atom, you know the number of electrons. and that's also going to be the same as atomic number. To get mass number, you add number of protons to number of neutrons, and you can rearrange this equation. Say you have mass number and atomic number, or mass number and number of protons, or mass number and number of neutrons. You can rearrange this equation to solve for what you're missing. For example, let's take oxygen. It has 8 protons, so its atomic number is 8. Not only is its atomic number 8, and that's the number of protons, but I'm talking about a balanced oxygen atom. So its number of electrons is also 8. If I had its mass number of 16 and I had its atomic number of protons, 8, I could do 16 minus 8 to get number of neutrons, which is 8. That's because I rearranged the equation mass number equals number of protons, or atomic number, plus number of neutrons to solve just for number of neutrons, which I was missing. If you're still confused about some of this information, there are linked videos. And there's also information about the differences between mass number and atomic weight in those videos. For now, we're going to stop there. Make sure to come back where we will review and continue on talking about molecules and compounds.